Okay, this video we're going to talk about infinity in my limits of integration. This is called improper integrals. So let's go for it. Now we're accustomed to this following kind of situation. We have a function like x squared and I can integrate it between the values of 0 and 1. And I get a solution of 1/3, right? Great. That's what it looks like. You're used to that. You should know how to do this. All is good here. Now what happens if rather than between 0 and 1, someone tells me between 0 and infinity? Well, of course, you think about it and you go, well, between 0 and 1, the area is 1/3. Between 0 and 2, the area is a lot bigger. Between 0 and infinity, the area is infinity, right? I mean, it's just going to keep getting bigger, so easy answer. The answer to this is infinity. True, that's correct. But when we have to calculate this, and there are many situations in which we will have to calculate this, we are going to use limits to be able to calculate it. So rather than writing it like this, I'll write it like this. Rather than putting infinity here, I'll put a letter here, for example, b. And I'll write the limit when b goes to infinity of the integral from 0 to b of f of x dx. And that's how I'm going to be doing it. Now, these type of integrals is just combining integration and limits. Nothing extraordinary about this. What you might find extraordinary is that actually some of these improper integrals that go to infinity will have finite answers. Let's take a look at one of them. Let's find this improper integral from 1 to infinity of 1 over x squared dx. So again, I write this using a limit. Great. Here, by the way, is the function. You can see it keeps getting smaller and smaller and smaller and smaller as x gets bigger, right? Well, let's just do the integration, and I end up with this thing here, and I solve the limit, and well, of course, as b goes to infinity, this part here becomes 0, so I end up with minus 1, which is 1, and that's my limit. So after I've solved the integration and I've solved the limit, the answer is 1. Hence, the area from 1 to infinity is not infinity, it's just 1. That's all it is. We get a finite answer. That area is finite. And it's very difficult to envision this. And there are many, many, many more situations in which you could get your mind blown thinking about how an infinite area happens in situations like this. It's kind of strange, but it's the mathematics of it. You get a finite answer, and the answer is 1. Great. Now, is this the only way we can solve improper integrals by using limits? The answer is no. We are going to be using very similar techniques to the ones we used to solve limits. So the first one we're going to be a comparison test. So remember the comparison test? We just compared the two limits to know whether the limit went to infinity or it didn't, and we had the squeeze theorem. So it's kind of similar to one of those. So I have a function, f of x, and I know that it's smaller than g of x. Okay, it's smaller than g of x whenever x is bigger than a certain value, like within a particular interval. Now, the integration from a to infinity of g of x, if that thing converges, since it's bigger than the other one, then the other one must also converge. However, the other way around, if f of x diverges and f of x is smaller than g of x, then g of x must diverge too. Now, this comparison test is something that we are going to be using to solve improper integrals. For example, we saw this one here, right? From 1 over x squared dx, we know that this thing converges to 1, right? So if this thing converges to 1, we know this thing converges, right? Great. Now, if I have this thing here, well, this is smaller than this because I'm always adding 1 here, so it's going to be a little bit bigger all the time. So this expression here is smaller. And since this thing is smaller than this, and this thing converges, well, I can conclude that this thing converges by comparing it with this one. Let's look at a slightly more complicated example. Prove that this thing diverges. Well, we have to find out something that's smaller than this, that diverges. And here's something that's smaller than this. Rather than having a 1, let's put an x, because I know that x is bigger than 1. So if I put an x here, I know that this thing is always smaller or equal than this thing. And this thing just becomes 1/2 once I cancel the x's away. So if I say f of x is equal to my expression here, and g of x is 1/2, well, f of x is always bigger or equal than g of x. Great. So if I show that g of x diverges, since f of x is always bigger, f of x must always diverge. So I'd simply do the integration, which is not going to be that difficult. It's going to be x over 2, and I get infinity, and hence f of x diverges. Well, that's the first techniques we're going to use for improper integrals. Remember, when one of the limits of integration is infinity. Thank you for watching. Goodbye.